This episode of The Deep Dive is brought to you by Wadadli Solar LLC, making sure your solar investment actually pays you back.
I want to start today with a bit of a visual experiment. I need you to picture the absolute cutting edge of the clean energy transition.
Oh.
You're driving down a highway, maybe out in the desert or across some plains, and you pass a massive utility-scale solar farm.
We've all seen them, yeah.
Exactly. Miles of sleek, dark blue glass shimmering in the heat, row after row, all tilting in perfect unison to follow the sun. It looks incredible.
Oh, absolutely.
It looks like something out of a sci-fi movie, right? Like it's run by a supercomputer deep underground, managing millions of data points every second.
It definitely screams high-tech. It's sort of the visual shorthand for the future.
Okay, hold that image. Now I want you to scrub it. Teleport back to 1985.
Wow, okay.
You're standing in a backyard in rural America. The grass is a little overgrown. Maybe there's a dog barking in the distance. And looming over the wooden fence is one of those massive white mesh satellite dishes.
Oh, the C-band giants.
Yeah, monsters. The
Yeah.
ones that look like they were trying to, contact alien life or something.
Or intercept Soviet communications, yeah. And just to be clear for younger listeners, we are not talking about the little pizza box dishes you see on roofs today.
No, not at all.
These things were enormous.
They were absolute beasts. Now, here's the premise for today's deep dive. What if I told you that those two things, the futuristic, shiny solar farm and that rusty, clunky 1980s TV dish, are, under the hood, basically the exact same machine?
It sounds completely counterintuitive. I mean, one is for watching HBO and wrestling, the other is for powering the electrical grid.
Right.
But we've been looking through this fascinating memoir from Alexis Lewis, a commercial solar expert who actually started their career back in the 80s building those satellite systems.
And the argument Lewis makes is just incredibly compelling. The thesis is pretty much, we haven't actually invented new physics for solar tracking. We just repurposed the old backyard satellite dish.
That is the key insight. The payload changed. We went from catching microwave signals to catching photons. But the problem of how do I point this thing at the sky and keep it there for 20 years, well, that hasn't changed at all.
So that's our mission today. We are going to debunk the idea that solar tracking is some mysterious black box software magic. We're going to look at the systems thinking that connects these two eras. And honestly, I was surprised by how much of this just comes down to simple geometry rather than complex code.
It really is a case of the more things change, the more they stay the same.
So let's start with the old school. Lewis paints a really vivid picture of working with their father in the mid-'80s, and this was not a buy it on Amazon and plug it in situation.
Not at all. This was heavy civil engineering in a residential backyard. Lewis mentions these were 16 to 20-foot parabolic antennas.
20 feet, that's like 2 stories tall.
It's a massive sail. You know? Just think about the wind load on a 20-foot dish. If a storm comes through, that thing catches the wind like a parachute.
Oh, yeah.
If you don't have that thing bolted down into some serious concrete, it is going to end up in the neighbor's living room.
Lewis emphasizes that they were building these from the ground up, importing raw aluminum, drilling holes, assembling the frame. It was a nuts and bolts operation. But I want to drill down into the tech because there are a few components Lewis mentions that I think a lot of us have heard of, but maybe don't actually know what they do, specifically the LNB.
Right, the LNB or low noise block.
It sounds like a wrestling move. He's coming off the top rope with the low noise block.
It does, doesn't it? But it's actually the most critical piece of electronics on the dish. If you look at any satellite dish, even the small ones today, it's that little arm sticking out from the center pointing back at the dish.
At the focal point.
Exactly. And in the 80s, its job was incredibly difficult. It was trying to catch extremely weak microwave signals that had traveled 22,000 miles from a geostationary satellite.
22,000 miles.
Right, so the signal starts strong, but by the time it hits that backyard in Ohio or wherever, it is barely a whisper.
Wow.
The dish acts like a big ear trumpet to collect that whisper and focus it onto the LNB.
So the LND is the ear.
It's more like the inner ear. It has to amplify that whisper without adding noise or
Yes.
static. That's the low noise part.
Okay.
But then, and this is the cool physics part, it has to downshift the frequency.
Downshifts it, like slowing down a recording.
In a way, the signal coming from space is a microwave frequency. Really high pitch, electrically speaking.
Yeah.
Your standard coaxial cable, the wire that runs into your house, it can't handle that frequency. It would just dissipate.
Oh, okay.
So the LNB acts as a translator. It takes the high-frequency space signal, converts it to a lower frequency, and then sends it down the wire to your receiver.
So it's taking a language the cable can't speak and translating it into one it can.
Precisely. And then you have the feed horns, Lewis mentions.
Which, again, sounds like something on a semi-truck.
The feed horn is basically a funnel. It sits right in front of the LNB. Its job is to illuminate the dish aperture.
Illuminate. Like a light.
Yeah.
In radio physics, yeah. It ensures that the LNB is looking at the entire dish surface to gather the maximum amount of signal, but not looking past the dish at the worn ground, which would create noise.
So it's all just geometry.
It's pure geometry.
Okay, so that's the brain and the ears. But the muscle is what really links us to solar. Lewis talks about the linear actuators.
And this is the bridge. A linear actuator is basically a motor that pushes a rod in and out.
Okay.
Think of it like a mechanized car jack. It converts spinning motion from a motor into straight line pushing or pulling. In the satellite days, this was the physical component pushing that massive 20-foot structure across the sky.
And they weren't just pushing it randomly. This is where the story gets really cool for me. Lewis highlights a company called Paraclips that was famous for its mount design. They used a cast half-circle polar mount?
The polar mount. This is a brilliant bit of engineering that solves a really complex problem with simple geometry.
Now, I know what a circle is, and I know what a mount is. But polar mount sounds like we're going to the Arctic.
It's actually about the geometry of the Earth. So all the TV satellites are in what we call a geostationary Clark orbit. They're all parked in a line directly above the Earth's equator.
Okay, so they form a ring around the middle of the planet.
Right. But because you are standing on the curved surface of the Earth, say in North America, that ring of satellites looks like an arc in the sky. It curves.
So if I want to point my dish at HBO and then move it to point at ESPN, I can't just move it sideways.
No.
I have to move it sideways and a little bit up or down to follow that curve.
Exactly. Which requires two motors, complex coordination, and a lot of math.
Oh.
Unless you use a polar mount.
Which does what?
You align the mount's axis with the Earth's axis. You literally point it at the North Star.
No way.
Once you do that, the geometry cancels out. You can use just one motor to sweep east to west, and the dish will naturally follow the perfect curve of the satellites.
That is so elegant. You solve the math with the metal, not the motor.
Exactly. It simplifies the movement down to a single actuator.
But here's the question that bugs me. Today, we assume everything has GPS, Wi-Fi, LiDAR. In 1985, how did the dish know where it was? How did it know it was pointing at the Galaxy 1 satellite and not just staring at empty space?
This is where the retrotech is surprisingly clever. It was a closed loop of mechanical logic. Lewis lists the components: sensors, limit switches,
Magnets.
motors,
Magnets.
simple magnets on the motor shaft. As the motor spun, the magnets would pass a generic reed switch sensor. And every time a magnet passed, click, click, click.
So it's just counting.
It's just counting pulses. The controller inside the house didn't know about orbits or physics. It just knew that HBO was stored at position 500.
Ah.
When you press the button, it powered the motor until the counter hit 500, and then it turned off.
It's dead reckoning. It's counting its own footsteps.
Precisely. And they had limit switches, physical buttons at the ends of the track.
Yeah.
If the dish went too far, it physically hit the switch and cut the power.
No software crash, no blue screen of death.
Just a physical stop.
That's it. And that's the point. I love that line from the source. They didn't overcomplicate it because they couldn't.
And that simplicity is what made it durable. It didn't need a firmware update.
So fast forward 40 years. Lewis is now in commercial solar, managing construction and operations for these massive energy projects. And they look at a modern solar tracker, one of those sleek robots we visualized earlier, and they have this realization.
It's the Spider-Man meme,
Yes,
where they're pointing at each other. It's the same thing.
it is. And this is where we have to strip away the marketing. If you go to a solar trade show today, you'll hear about AI-driven algorithms, cloud predictive modeling, machine learning optimization.
Right, follow those words.
And sure, that exists in the background. But Lewis argues that if you look at the fundamental machine, a solar tracker is still just four things.
Let's run through that list because it really demystifies the tech. Number one, a structure.
The metal racking holding the panels, just like the mesh dish, it's steel in the ground.
Number two,
We interrupt this podcast with a quick reminder. Solar systems that aren't inspected don't perform as designed. Annual inspections protect output, safety, and payback. Wadadli Solar LLC, serving the U.S. Antigua, Guyana.
a drive mechanism.
The motor or linear actuator? The muscle. Number 3, control logic.
The brain that tells the muscle when to move.
And number 4, known celestial movement.
And that is the constant. The satellites in 1985 were geostationary. They stayed in one spot relative to the Earth, or at least in a predictable arc.
Right.
The sun is also predictable, doesn't jump around. We know exactly where the sun will be at 2:00 p.m. on a Tuesday in October 10 years from now.
Because the target is predictable, the machine doesn't need to be a genius. It just needs to be punctual.
Exactly. You aren't tracking a fighter jet that's taking evasive maneuvers. You're tracking a giant ball of fire that runs on a very strict schedule.
This brings us to the deep dive on how solar trackers actually think. Because even though the target is predictable, Lewis points out there are two different philosophies on how to follow it. It's the open loop versus closed loop debate.
Right. And this is a huge topic in solar engineering. Let's start with closed loop, which is often called sensor-based tracking.
Is this the sunflower approach?
That's the perfect analogy. In this system, you put a little photosensor on the tracker. It looks at the sky and measures irradiance, the intensity of the light.
Oh.
It effectively says, it's brighter over there to the left, and sends a signal to the motors to move the panels until the sensor says, okay, now we are dead center.
That sounds intuitive. Why wouldn't everyone use that? It seems like the most accurate way. If the sun is there, look there.
It is accurate, but it's reactive, and the world is messy. Imagine a partly cloudy day. You have big, bright, white cumulus clouds.
Okay.
Sometimes the brightest spot in the sky isn't the sun itself. It's a reflection off the edge of a bright cloud.
Ah.
The sun might be momentarily blocked, but the cloud next to it is glowing white hot.
So the sensor gets tricked.
It gets tricked. It starts hunting.
Yeah.
It moves left, then right, chasing the brightness. That wastes energy,
All right.
and more importantly, it wears out the motor.
You're just cycling it back and forth for no reason?
Exactly. Plus, I imagine things get dirty. Huge problem. Bird droppings, dust, snow. If a bird lands on the sensor, suddenly the system thinks it's nighttime or that the sun has moved 90 degrees.
So what's the alternative, the open loop?
Open loop is the astronomical or time-based approach. The system doesn't have eyes. It doesn't look at the sky at all. It relies purely on math.
It's introverted.
Totally.
Yeah.
It has a microchip with an algorithm that calculates the sun's position based on your specific GPS coordinates and the exact time of day.
So it's like a schedule.
Right. It just says it is 10:00 m. The sun must be at an azimuth of 135 degrees, and it moves there.
It doesn't care if it's cloudy.
It doesn't care if there's a blizzard. It doesn't care if a bird is sitting on the panel. It knows where the sun should be, and it goes there.
That sounds like the satellite dish logic again. The satellite dish didn't look for the signal visually. It just counted the clicks to the right position.
Exactly. Lewis notes that both systems work, and modern trackers often use a hybrid. But the open loop relies on that same confidence in geometry that they used in the 80s. It's trusting the physics over the feedback.
Let's talk about the hardware again, because when we talk about solar fields, we usually see those long rows, miles of tubes. Lewis compares this explicitly to the old polar mount.
This is what we call the single-axis tracker. It's the workhorse of the solar industry. Imagine taking that Paraclips dish mount, which rotated east to west, and just stretching it out into a 300-foot-long tube.
Okay, stretching them out.
You mount 50 or 60 solar panels on that tube, put one motor in the middle, and the whole row rotates together to follow the sun from morning to evening.
One motor for 50 panels?
Sometimes one motor for huge blocks of rows linked together by drive shafts.
Yeah.
It is optimized for scale. It's simple. It creates that polar arc movement.
But just like the satellite days, you're limited. You are only rotating on one axis.
Exactly.
Which means you can't tilt up or down. But the sun does move up and down depending on the season, right?
Yeah.
It's lower in the winter, higher in the summer.
Correct. A single-axis tracker ignores that up and down shift. It accepts that it won't be perfectly aligned in the winter or summer.
That seems inefficient.
It's a calculated trade-off. We call it cosine loss. You lose a little bit of power because you aren't perfectly perpendicular to the sun.
Right.
But the industry decided that losing that small percentage is worth it because the machine is so much simpler.
But there is a version that does do both, right? The dual-axis tracker?
For Ferrari of trackers, Lewis mentions these are often monopole mounted, which makes them look almost exactly like the old satellite dishes.
A big pole in the ground.
A big pole in the ground with a mechanism on top that can spin 360 degrees, that's the azimuth, and tilt up and down, that's the inclination.
So it's always perfectly perpendicular to the sun. It's like a sniper rifle for photons. It's squeezing every last drop of energy out.
It is. But here is the rub, and this is the core engineering lesson from Lewis. Why don't we see dual-axis trackers everywhere? If they produce more power, shouldn't they be the standard?
I'm guessing the answer is money.
Money and reliability, Lewis points out. Dual-axis means two motors, two gearboxes, more complex controls, more failure points. In the satellite world, you needed that precision. If you were off by a fraction of a degree, you lost the signal completely. The screen went to static. You missed the Super Bowl.
The high stakes.
Exactly. But in solar, if you are off by 2 degrees, or if you ignore the seasonal tilt, you lose maybe 1% or 2% of your power output. It's not catastrophic. The lights stay on.
Right.
So the industry asked, is it worth doubling the maintenance cost, doubling the motors, and doubling the risk of breakdown just to get that extra, say, 10% of energy?
And the answer was no.
Almost always, no. The single axis, the simple, reliable, good enough geometry won the war. It's the Periclipse logic applied to a power plant.
This brings us to the philosophy of systems thinking. Because Lewis isn't just giving us a history lesson here. They are arguing that the lesson learned in that backyard in 1985 is the most important lesson for engineers today.
Right. It's easy to get obsessed with the component. The newest solar panel with 24% efficiency, the fastest microchip. But Lewis says you have to look at the system.
The whole thing.
Right. Tracking is a system of geometry, timing, motors, feedback, and reliability.
I like that list. It takes the magic out of it and puts the engineering back in.
It poses the universal challenge. Whether you are pointing a dish at a satellite or a panel at the sun, the problem statement is, how do I move a heavy metal structure accurately, repeatedly, and safely outdoors for 30 years?
That 30 years part is the kicker. It's not about whether it works on day one. It's about whether it works after a decade of rain, snow, grit, and wind.
And that's where the smart technology often fails. If you have the most advanced AI tracking algorithm in the world, but your linear actuator rusts out in year 5 because you didn't account for humidity, your system is a failure.
It's a brick.
It's a very expensive statue. The dumb mechanical integrity matters more than the smart software.
Lewis has this great line that really stuck with me. The technology evolved, the physics didn't.
It's a powerful mantra. We often get distracted by the payload. We think, oh, this is a solar panel, it's a semiconductor, it's high tech. So we assume the mounting system must be space-age technology too.
Sure.
But physically,
yeah,
it's just a sail catching the wind.
it's a 20-foot dish wearing a different outfit.
Exactly.
Yeah.
And looking at it that way helps us solve problems better. If we understand that the sun's movement is just as predictable as those old satellites, we realize we don't need to reinvent the wheel. We just need to build a really sturdy wheel that turns when we tell it to.
I think that's such a refreshing perspective. It takes the intimidation factor out of renewable energy. When you drive past that solar field now, you don't have to wonder what the black box is doing.
Right.
You can look at it and say, hey, that's just a linear actuator pushing a lever.
And you can appreciate the elegance of it. It's not smart because it's complicated. It's smart because it's simple.
Simple, precise, and durable. Just like that Periclipse mount in the backyard.
It stood the test of time for a reason. And honestly, if you go out to some rural areas, you can probably still find some of those old mesh dishes standing there.
Probably covered in vines, but still pointing at the Clark belt.
Exactly.
So we've gone from the backyard of the 1980s, importing raw aluminum and LNBs, all the way to the massive utility-scale solar fields of today. And the thread connecting them is Alexis Lewis's insight that the physics never changes.
It's a testament to good engineering principles. If it worked to catch a TV signal from space, it'll work to catch sunlight.
Before we wrap up, I want to leave you, the listener, with a thought. We live in a world that is obsessed with the next big thing. We love to add layers of digital complexity to everything. Wi-Fi-enabled toasters, AI-driven toothbrushes.
We assume that smart always equals digital. We think if it doesn't have an app, it's obsolete.
But Lewis's story forces us to ask, if the physics hasn't changed in 40 years, why do we insist on overcomplicating the solution? When you look at a problem in your own work, whether it's energy or logistics or just organizing your day, are you trying to solve it with complex software when the answer might just be simple geometry and a reliable motor?
That is the million-dollar question. Sometimes the old-school approach isn't outdated, it's just optimized.
Something to think about the next time you see the sun moving across the sky. That's it for this deep dive. Thanks for listening.
Thanks, everyone.
Thank you for listening to this podcast. We hope you found this podcast useful. If you have any questions or comments, feel free to reach out to us at info@alternativesolutions.ag. Thanks again for listening, and be sure to tune in for future episodes.